Thank you very much for the invitation. It's a pleasure to be here. So today I will I will talk about I will give an overview about some work that we've been doing at KTH during the years, and the main tool I will describe it's this stable ranks that we've been developing and applying in several contexts. For example, the classification of microglia morphologies. So microglia are immune cells in the brain. And after showing like how these tools can actually be applied to data, I will describe how one can do more sophisticated analysis with parameterized, by choosing within parameterized families of stable ranks. Feel free to interrupt me at any point if you have questions, and we'll get started. So I assume you are somehow familiar with the topological data analysis ideas, but I will just give a quick review of the pipeline. So the idea is that we start from data. Data could be in the form of a point cloud, so a set of points in R to the n, or it could just be a metric space. We know distances between points. It could be an image. It could be a simplicial complex constructed from data with some function defined on it. There are many different types of inputs that we can take in TDA. And these are usually discrete objects, and we want to understand their structure by approximating them with a sequence of simplicial complexes. If this is a metric space, a point cloud, then what one can use is, for example, Vietoris Rips to construct this sequence of simplicial complexes. So this construction is just a way of highlighting geometric structure in the data, but does not simplify the information we have up here on the original data. So the idea is to then apply homology and obtain instead a sequence of vector spaces and linear maps between them. These are actually the main object of study from an algebraic perspective in TDA. So these sequences of vector spaces and linear maps. They are usually used in or described through barcodes, persistence images here on the right, other types of vectorizations. So for example, persistence landscapes, or also the stable ranks. That is what we are working on. It's the middle one. So more formally, this sequence of vector spaces and linear maps, one can see as a functor indexed by R and with values in vector spaces. And we consider functors from R to vector spaces and maps between them, so natural transformations between them. So we have for each V a map from FV to GV, and these maps have to commute with the internal maps of the modules. And people usually restrict to the category of tame persistence modules. And this means that there are finitely many critical values. So there are finitely many points where these sequences change, finitely many points where these maps are not isomorphisms. Okay, and I showed you the pipeline to get a functor indexed by R, but it is more and more interesting to find actually multi-persistence modules, and there are constructions that provide them. So for example, if one has a data set and two functions of interest on this data set, not just one. In this case, one obtains a bifiltration or a multifiltration and a functor indexed by R to the R. Let's say that the pipeline I described before proceeds smoothly until the algebra, so I can build this multifiltration of simplicial complexes, that is a functor from R to the R to simplicial complexes, apply homology, no problem, and I obtain this functor with values in vector spaces. The problem here is that there is no natural barcode decomposition for such functors. So if one looks at the commutative algebra perspective of this, these are equivalent to modules over the polynomial rings, graded modules over the polynomial rings in R variables. So the structure theorem that exists in one variable does not exist in several variables. So such a barcode description that is so much used in a one-dimensional case is not available here, and there is a need to find new invariants. And this is what actually motivated our definition of the stable rank, which can be well defined also in the R to the R poset case. Again, also in the multi-parameter case, we are interested in the category of tame functors, which means that these functors are constants in some regions of the parameter space intuitively. So one can find a grid in N to the R, which discretizes this, and then the real functor is a Kahn extension, a left Kahn extension of this functor from N to the R. This is important because, at least for us, because we want to find invariants that are based on the number of generators. So we actually want functors which are finitely generated. Okay, in particular, we are interested in the rank. These tame persistence modules, which are actually modules over the polynomial ring in R variables, have a finite projective dimension. One can build minimal free resolutions of them and compute multigraded Betti numbers that are the number of free functors that you have at each step of the resolution in the various degrees, and also the rank. So the rank is the zeroth Betti number. So the number of free functors you need at the first step of a minimal free resolution, or equivalently, the minimal number of generators of the persistence modules from the algebraic commutative algebra perspective. In the one-dimensional case where we have this barcode decomposition, the rank is the number of bars in the barcode decomposition. So it's a quite simple descriptor of the persistence module. You can think it, the number of bars in the barcode decomposition. The problem with this descriptor, which can, however, be computed algorithmically, it's that it's, first of all, very discrete, and then it's not stable in the sense that one can perturb the data a little bit, for example, perturb the function on a simplicial complex with a very small L infinity perturbation, and then the rank can change a lot. So we don't have this idea that small perturbation on the data induces a small perturbation on the description you give. So we thought about this workaround, and this is the main ingredient of the whole story, and it's called a stable rank, and it works with this idea of hierarchical stabilization, which at the same time appeared in a slightly different context in a paper by Willbauer and co-authors. So the idea of hierarchical stabilization is that you have a functor and you have an invariant on the functor, for example, the rank, minimal number of generators. This is discrete, but you want to make a function out of it. And the function you define is piecewise constant and non-increasing, and it's defined in the following way. So the value in 0 is actually the value of the invariant on your module, so it's the rank of f. And then for each t, you take a metric neighborhood of your functor f and minimize the invariant, the rank, in that metric neighborhood. So since the neighborhoods are bigger and bigger, the invariant gets smaller and smaller. This is why it's piecewise constant and a non-increasing function. Okay, so I said that you take metric neighborhoods, and this is something that we have to think about. So the stable rank takes as an input a persistence module and a distance to compare persistence module. It's not just an absolute measurement on the module, but it says how this module compares to others, to all others that are possible. So for for any distance, you obtain a different stable rank. For each distance that I choose on persistence module, I get a different function. And this is something we will talk about more later on. But first, I want to describe why we call it stable rank. We obtain these functions that are piecewise constant and non-increasing, and there are many distances one can have on functions. One, for example, is this interleaving distance, and it's defined in the following way. So we say that two functions which are non-increasing are epsilon interleaved if f of v is greater or equal than g of v plus epsilon, and vice versa, g of v is greater or equal than f of v plus epsilon. And then we take the infimum such that f and g are epsilon interleaved. So in this figure, the distance between the orange and the blue one would be the length of this arrow. It's how much one function is below the other. It is not difficult to prove that the stable rank is a one Lipschitz function. So it's a Lipschitz function with constant 1 from the space of same persistence module to this space with to this space of non-increasing functions with interleaving distance. So this is the stability result that we were aiming for, and why we call it also stable rank. So if I have a small error between f and g, a small distance between f and g, and then I compute the stable ranks to simplify f and g, then the interleaving distance between them will also be small and smaller than the distance we have in the beginning. This is what we aim for when we talk about stability. So we transformed this discrete invariant, the rank, that was not stable into a stable one, which are these functions. Okay, now I have described this idea of the invariant we want on the persistence modules and therefore on the data. And I said that it's important to have a distance to define it. But I didn't still explain which are the distances that we can have on the persistence modules or on these persistence modules with R to the R as indexing poset. Actually, at the time we started working on this in 2017, there was just one distance there. It was the interleaving distance by Lesnik, but this construction generalizes that. So the idea, and here we will start a big parenthesis, is that we want to define a distance by defining what is a small. So this idea of noise system. We want to define what is the size of a persistence module, how small that is, and then collect persistence modules according to their size. And this will be the building blocks to build distances after. So what is a noise system? So we fix epsilon, and we define noise systems axiomatically. We say that noise of size epsilon is a set of persistence modules, and 0 belongs to S epsilon for any epsilon. So 0 is arbitrarily small. And S epsilon is the set of modules which are at most epsilon small. So they are epsilon small or smaller. So these sets are closed under inclusion. If tau is smaller than epsilon, then S tau is contained in S epsilon. S epsilon contains all the modules that are noise of size at most epsilon. And then here there is a condition about exact sequences. So if I have a short exact sequence of modules and the G is in S epsilon, then also F and H have to be. So if I have a submodule or a quotient of a persistence module that is epsilon small, then they also have to be small. I think that submodules and quotient reduce the size. And if F is in S epsilon and H is in S tau, then G have to be in S epsilon plus tau. If G is built up in the sense of a short exact sequence by something that is of size epsilon and tau, then this has to be at most size of epsilon plus tau. So these are the axioms And one asks, okay, but can I find examples of this? Here I have a figure of a matryoshka by saying that the second axiom, so they are nested one into each other, these noises. Okay, can we find an example of this? Yes, so this is a business that has been running since we defined this, and I'm always looking for new types of noise systems with the conviction that noise is context dependent. So there is not a universal choice of distance that one wants to have between persistence modules and in general between data, but the distance and therefore what has to be defined as noise depends on the problem of the application. But here are some abstract definitions, and they will become more practical later on. So for example, a generalization of interleaving distance by Lesnik is this standard noise in the direction of a cone. One can choose a cone of direction in R to the R, and then say that a module is epsilon small if for every V, so every point in the parameter space, and for every X in f of V, there is a direction in this cone and a vector of length at most epsilon such that X is in the kernel of the map from FV to FV plus W. Here is an example. So if, for example, I take this persistence module here, and as a direction, as a cone, I take the diagonal, then this module here is considered to be 1 small if the size of this arrows is 1. Because if I take the image of each element of the module, and in particular it's enough to look at for the generator, and move it in the diagonal by 1 in infinity norm, then every element has image 0. So if I push every element in the module in the direction of the diagonal by 1, then all these elements have image 0. Let's say that it's quite important to have morphism in this context, because this noise system really tells you about the image of the module with respect to a shift in some direction. A completely different type of noise system that was defined by my master student last year, Daniel Lundin, is the volume noise system. So here we are not looking at maps, at the images of the generator with respect to maps in the persistence module, but we are looking at the domain, just the positions in the parameter space where the module is non-zero. So we can define the domain and say that something is epsilon small if the volume of its domain is smaller or equal than x. So if it's concentrated in an area of size at most epsilon. Or a slight generalization of this, one can integrate the dimensions of the vector spaces within the domain, and this has to be smaller or equal than epsilon. So one can prove that all of these examples follow the axioms of noise systems. In particular, there is for the one-dimensional case, so for when R is equal to 1, there is one more example that is quite interesting for the TDA. And this is the one of the p-norm, which was initially defined by K. Turner and Primož Skraba. So given a module with a barcode decomposition, so here it's important that we are in one dimension, one can define the norm of the module as the p-norm of the length of the bars. So for finite p, we just take the p-norm of the length of these bars. And with Jens Ageberg, Andrea Guidolin, Isaac Wren, we were able to give a proof, an explicit algebraic proof, that this norm actually defines a noise system. Okay, so we have seen a number of noise systems, and I will define one more because I'm actually interested in parameterized families of noise systems. Already the one I described before, here the p-norms is parameterized by p. So for each p, we have a different p-norm. Another type of noise system is one defined by contours. And these have been defined by Wojtek Hachulski, Henry Riechimaki, and Oliver Guthbert. In the one-dimensional case, they can be described as follows. So we have a lax action of the monoid 0 infinity on the poset 0 infinity. So if I act by 0 on A, I stay in A. If I act first by epsilon and then by tau, it's the same as acting by epsilon plus tau. And if A is smaller than B, epsilon is smaller than tau, then the action of epsilon on A has to be smaller or equal than the action of tau on B. So we can take the set of functors that are tail and that the maps from f of v to f of cv epsilon is the zero map. And this forms a noise system. So this is a generalization of the standard noise, but we don't flow in the parameter space by going from v to v plus epsilon, for example. So we don't flow with a vector of length epsilon, but rather with this contour, which, as we will see later, gives us a way of moving faster or slower in different parts of the parameter space. So for each v, we can move in a different way in the parameter space. In particular, if we add these two technical conditions here, that in the first variable and the second variable, it is a monomorphism, plus in the first variable, then the image is A plus infinity, one can define a so-called lifespan, because these contours are regular. But before saying what a lifespan is, I just give you examples of contours. So there are very many contours. There's a very rich space of contours, and they are parameterized by measurable functions. I said I was interested in parameterized families. Here we have very rich parameterized family. For each measurable function, I can define a contour, and the contour is defined as follows. So I start from A, and I want to move by epsilon. The value of the contour, df, this distance type contour associated to the function f, is how much I have to move on the parameter space to achieve an area under the curve given by f of epsilon. So I want to find the value such that the integral from A to that value of f is equal to epsilon. And then if f is the constant function, this is just the sum. Okay, so I anticipated the idea of lifespan. For a regular contour, which is the one I defined before with the extra assumptions, one can define the lifespan of a bar BD as the unique non-negative real number L, such that if I act with L on B, I obtain D. If I take this standard contour, that is just A plus epsilon, then the lifespan is the length of the bar. So we are trying to generalize this idea of length of a bar, but with a non-uniform weight on the parameter space. This contour tells us how we flow on the parameter space. So in particular, in this example, if I take this function f and I have a bar from B1 to D1, its lifespan will be all this area L1. So this will be how much this bar weighs. But if I take a bar from B2 to D2, which is actually of the same length, its lifespan will be this area L2, so it will weight less. Okay, this idea of lifespan is interesting on top of the idea of constructing noise systems based on contours, because with the proof we gave about the p-norm, one can define the p-norm associated to a contour, so a PC norm, and substitute the length with the lifespan and take the p-norm of lifespans of bars. This is a generalization of the p-norm we defined before, and the same proof follows that this is a noise system. So in this case, we have two different types of parameters, and we will discuss them later. The P of the P norm and the C, the parameters involved in the contour. Okay, so I defined noise systems axiomatically and gave some examples. So we have some examples of noise systems. What actually matters on top of these axioms are some properties of noise systems. For example, one property that is important or useful actually for algorithms is the one of being closed under direct sums. So we say that a noise system is closed under direct sums if every time two functors belong to S epsilon, then their direct sum also belongs to S epsilon. Contour noise systems, so the standard one plus the ones with contours, are examples of noise systems which are closed under direct sums. P-norms, volume noise systems are not. So for those, we have to find different strategies. Here is just an image of some examples of noise systems I have described as a summary. So we have the P-norm with the contour, these contour noise systems, which I call here simple noise system. Then we have domain, dimension, the volume. There are very many types of noise systems one can define. So this was a big parenthesis about noise systems and how to define the norm, a norm, let's say, and it's also called amplitude norm or the size of a persistence module. Now, noise systems can be used to define distances between persistence modules. And the way this can be done is as follows. So we have F and G and a noise system, and we say that F and G are epsilon closed if there exists another persistence module H with maps to F and G, such that the kernel and co-kernel of these maps are noises whose values sum up to epsilon. One can prove that under the axioms of noise systems, then this actually defines a pseudometric on tame persistence modules. If we take the infimum, so the infimum epsilon such that F and G are epsilon closed, this is a pseudometric. And this can be proved just with the axioms of noise systems. So actually, we recently realized that instead of the sum, one can also take the p-norm of the contributions of kernels and co-kernels, and this also defines a pseudometric, and it coincides with this algebraic Wasserstein distance that was introduced by Turner and Scraba, and identified with Wasserstein distances, which are usually used in TDA to compare persistence diagrams. Okay, so for each noise system, now I have a distance to compare persistence modules. Or a pseudometric, actually, it's not really a distance. And sometimes I just want to compute distances between persistence modules. Sometimes it's actually better to compute stable rank, use a stable rank, or even better, consider angles between stable ranks. So one can consider stable ranks in a Hilbert space. These are functions, so you can consider a scalar product and integral of the scalar product between them. And this is the definition of the stable rank kernel. So given two persistence modules, X and Y, their stable rank kernel is the integral of the scalar product of the corresponding stable ranks. Now I have described a pipeline that goes from noise systems to distances, and from distances to invariance in the form of stable ranks. The most complicated part is the computational part. So these distances are usually very difficult to compute, and in some cases they have also been proven to be NP hard. But not only the distances are difficult to compute, but also the stable ranks are difficult to compute. So here is the mathematical the mathematical contribution that is needed, like to find algorithms for computing distances and stable ranks given type of noise system, and this is where we are working. But for one persistence, actually the stable rank computation, if we consider a noise system given by a contour, is very easy. It's very simple. And this is mainly given by the nature of one persistence that has a barcode decomposition. So this functional summary, this piecewise constant function at step t has value the number of bars whose lifespan, according to the contour, is greater than t. So in the end, this function is a functional summary of a histogram of the lifespans of the bars in a barcode decomposition in the one parameter case. Okay, so in this one parameter case, we know how to compute distances, we know how to compute the stable rank, and they can be used in application, especially through this kernel, which can be combined with kernel methods in machine learning. And now I will describe one application of this. The application is to understand rooted trees with a function defined on the nodes. And so the application is to topological morphology descriptor that was defined by Lida Canari in her PhD thesis. So we can consider a tree that is rooted and that has a function defined on the nodes of the tree, function with values in R. And the TMD is an algorithm, a linear time algorithm that produces a persistence barcode starting from this tree. In this persistence barcode, every bar corresponds to a leaf. So for each leaf of the tree, we have a bar, and bars stop when leaves connect to each other through branches. So under certain conditions, one can think of this as a super level set persistence. So one can look at outside every circle, decreasing circles, how many components you have, the H0, and the maps between them. And this determines this barcode. Otherwise, combinatorially, one can consider leaves, their parents, and check for each parent how many children there are, at which distance, also which value of the function these children appear. These are bars, and then when two children merge in the parent, one of the two bars stops and the other continues according to the elder rule. So this is the combinatorial approach, which takes into account parent-child relation and the function on the nodes too. Here is a slightly different representation of the persistence barcode. It's a persistence diagram where each bar is represented by a point in the plane with coordinates the birth and the death of the bar. So this algorithm was designed by Lida to study neurons, so neuronal cells, and it worked very well. So here is a very simple example where we have neurons coming from different species. So this is not a difficult classification task. The species are cat, dragonfly, fruit fly, mouse, and rat. But one can see how the TMD captures properties of these trees, which are important for the classification. So for example, here we see that this barcode has two parts that are two parts of the parameter space that are densely populated, while in example 2, the bars are distributed all over the place in the parameter space. So this property of having just two parts in the parameter space which are densely populated corresponds to the neuron having a tuft ahead. So that is a property that is important for its classification in terms of structure. So in this case, we can see that these persistent barcodes capture properties of the trees which are relevant to their shape and then also their function actually in the brain. And this morphology descriptor has also been used for finer classification of pyramidal cells in the mouse brain. I was working on this project addressing problems of stability of this algorithm. So we checked that if we perturb the data a little bit by perturbing the position of the nodes or adding small branches, then the output doesn't change much. But at the time, we didn't face a problem, data analysis problem quite common that actually came up later in microglia classification. That is that the data is very variable. So the data changes a lot within classes. There is an intrinsic variability in the data. It's not homogeneous. Classes are not homogeneous. So this leads to this project with Sandra Siegert's lab at IST, us at KTH, and then the Blue Brain at APFL with Catherine Hess and Lida Canari, where we have used stable ranks, TMD, to study microglia cells. So Sandra's lab reconstructed a fantastic data set with more than 40,000 microglia morphologies from images from the mouse brain. And from different regions, different sex, or also mouse under development and under some, and with respect to some degeneration model too. But here I will focus just on different regions, just to give a taste of the analysis we did. So I described before the TMD that given a rooted tree assigns a barcode and then a persistence diagram. One can then consider persistence images associated to this persistence diagram by considering Gaussian kernels on the points of the persistence diagram. And it was observed that on the average, different groups had sort of different persistence diagrams, but this was not seen at the individual level of trees. And this again is because the data is has a strong intrinsic variability, because these microglia morphologies move a lot according to cues in the environment. So their shape can change a lot. And so in this case, Ryan and Sandra's group, they proposed a bootstrapping method, which is actually well used and well known in statistics, but we used it on persistence image and stable ranks. The idea was to subsample the data and then take averages of these samples. And with these bootstrapped samples, we were able to see with UMAP that actually microglia coming from different brain regions were quite separated. And this was very, very interesting for the biologists, because this was not known before. So the ability of making averages with topological data analysis summaries was fundamental here. We also did it with stable ranks and obtained a similar image on the UMAP, similar separation. So rather than persistence image, we took stable ranks with standard contour. And actually doing it with the stable rank also allowed us to understand which part of the persistence image, which characteristics of the data were important for the separation, because the stable ranks are not complete invariants of the persistence model. They just take information about persistence. And through the stable rank kernel, we were able to do pairwise classification and actually test that the visual intuition that came with UMAP brought to according classification accuracies with a support vector machine and the stable rank kernel. We were also able to play a bit with these parameters of the bootstrap and see how much of the signal was given by the average and how much of the signal was already there in the raw data. So this is an example of practical use of the basic stable rank in application. The last part of the talk, I would like to discuss a small theoretical contribution which would allow to a more detailed, sophisticated analysis, for example. So I said that computing stable ranks is generally very hard, especially in the multi-parameter case. In the one-parameter case with contours, it's actually easy. What about the one-parameter case with this PC Wasserstein distances? So if we take the Wasserstein norm of the persistence module with a contour and the distance defined by that. So we've been working on finding an algorithm for computing the stable rank with respect to these distances, and found a strategy. So we found that, as I said, to find the distances, we have to find a witness h between f and g. And in this case of finding the stable rank, we were able to prove that the stable rank is the minimum rank among all g that fit into a mono epispan of this type. And g is in the neighborhood of f at distance t. So in particular, what we were able to do is to reduce to mono epispans. Instead of looking at all g that are at distance t, we could just restrict to all g that were linked to f via mono epispan. This was the first step. And then the second step, and actually the most important, was to prove that for each mono epispan, there is a bar to bar one, which has a smaller or equal cost, so at a smaller or equal distance. These bar to bar morphisms are morphisms that map each bar in a barcode decomposition to just one bar in the barcode decomposition. So these are maps that preserve the barcode decomposition in some sense, that send just bars to bars. You cannot send one bar, so one generator to two different generators in the other model. So in this way, we were able to figure out the points of discontinuity of these stable ranks with the PC Wasserstein distance. And they correspond to the p-norm of lifespans of bars. So we take persistence module and order its lifespans in increasing order. Then the ith discontinuity point of the function is the p-norm of the first ith lifespan with this factor here. And what is the value? It's n minus I. So this function decreases by 1 at a time with the p Wasserstein. And how much they decrease depends on the lifespan of the bars, or the length of the bars, if we take the standard contour. So it's actually very, once we have the algorithm, once we prove that this is the algorithm to get the stable rank, it's actually very easy to compute it. Okay. So just to give an intuition of what these PC stable ranks do on the data and what this parameter P and C mean, let's first look at the parameter P. Here is an artificial data set where we try to mimic a scenario in which, in this case, long bars don't follow the same distribution, and short bars follow the same distributions. So we make images and then take persistence of these images through cubical complexes. And it turns out that in a construction such that long bars don't follow the same distribution, while short bars follow the same distribution. So in this case, the long bars are the signal and the short bars are the noise. So we did a grid search and saw what is the best P that distinguishes these two scenarios. And it turns out, also according to our intuition, that it is P infinity. So a large value of P is better if the signal is in long bars. Instead, if we do the opposite, so short bars follow different distribution and long bars follow the same distribution, so the signal is short bars, and we do try to optimize the P with a grid search, we see that a small P is more appropriate for this classification task. So the intuition here that if the signal, what is important to figure out from your data is hidden in short bars, then a small value of P is more appropriate. And it's important to be able to learn this because we don't know a priori if it's long or short bars that contains information in the data. And finally, an example on a publicly available data set that was already used in this paper by Paul Bendich and co-authors. So this is a data set of 3D reconstruction of brain artery trees with individuals with age between 18 and 72. And this structure of the brain arteries was found to correlate with age, also through persistence summaries. So what we did was that we split the data into parts, class A and class B. I is the union of A and B, so I is all the data. A, age below 45, B, age above 35. And we tried to do a metric learning approach to optimize the parameter P and the parameters of C at the same time. In this case, C is a contour which is defined by a density function, the way I showed before. That is a sum of two Gaussians. So lambda is a parameter that weights the second with respect to the first, and then these mu's are the centers, and the sigma are the standard deviation of the Gaussians. So we have parameters mu, sigma, and lambda that are associated to the contours, and the parameter p that is associated to the p-Wasserstein distance. And in this case, we try to do a metric learning approach to see which were good parameters for this data set to distinguish class A and then class B. We didn't do a thorough analysis of the optimization problem, but over 25,000 iterations, we could see that usually this loss function that we defined, which minimizes distances within classes and maximizes between classes, the loss function goes down quite smoothly and the parameter P stabilizes. Also the parameters for the Gaussians stabilize. And here on the bottom, you can see what is the contour, the density we found for the contour. So which parts of the parameter space should be highlighted. It's worth noticing here that the parameter P stabilizes to 1. So this tells us that short bars play a role in this example. And this was already highlighted by Paul Bendich and co-authors with other types of analysis involving persistence. So in this case, small or medium-sized bars play an important role. Overall, just to recap, so this parameter P serves to weight short versus long bars importance in the barcode, and the parameter of the contour to weight which parts of the parameter space play a role in the classification. Here you can see again the contour, the density of the contour superimposed with some barcodes, and on an image of the data set how it looks. The idea is that highlighting parts of the parameter space which are important, one would like to highlight parts of the data which actually are important for the classification task. Another important observation was that we noticed that optimizing the parameter P and the parameters of the contours at the same time yield a better classification than optimizing them separately. So it's beneficial to actually look at the interplay of these two different types of parameters and optimize them together. And this overall brought in better accuracy. So if we do with k-nearest neighbor classification, after we have found an optimal distance, then this classifies the data better than what was found before. So overall, I hope I have explained that we have defined these stable ranks, and each stable ranks depends on a different distance, so it can pick different information on the data based on the distance you have. These stable ranks can actually be used if they can be computed efficiently. Well, they are very suitable for statistics and machine learning. So here are examples where we do dimensionality reduction, support vector machines, subsampling, but they can also be fed to neural networks, and this is another story. It's important to remember that one can vary the metric, and this offers a variety of different views on the data. And in particular, we like parameterized families of stable ranks, because so we can choose in this parameterized family in an optimized way, which is the best distance for the data set at hand. And then this will hopefully give some insight on the data itself. Okay, thank you for your attention. I would be happy to take questions.